So we assume that the semi-simple Lie group has a compact Cartan subgroup, and so let's call the subgroup B. Our aim is to construct an invariant eigendistribution corresponding to a regular character psi lambda on the compact Cartan. So we want to construct the distribution on all of G. But the formula for this is given just similar to the Weyl character formula. The formula is given only on the regular points of the compact Cartan. It has the same appearance. But on the numerator, the summation is only over the alternating sum, is only over the Weyl group of K, not the full Weyl group of G. So since we are dealing with a non-compact G, there will be non-compact Cartan subgroups. So it's not reasonable to expect that if you know the distribution on the compact Cartan, it has a unique, it is uniquely given everywhere else. No, it's not reasonable to expect that. For example, if you look at the unitary principal series, irreducible unitary principal series, all of them vanish on the compact Cartan, all of them. So there have to be some other ingredients which make the extension unique. So by imposing a growth condition which restricts the behavior of the distribution at infinity on the group, Harishchandra was able to assert that there is a unique extension. But let's see. An important additional observation must be made. The growth condition amounts to saying that the distribution must be tempered. But that only intensifies the mystery, because the principal series representation, they also have a tempered character. The distribution is tempered. And they're all zero on the compact Cartan. So that only intensifies the mystery. So what is the single most important, crucial ingredient which makes the crucial difference between that case and this case? So the point is that if you look at, it will be real on the Lie algebra. But in the case of Harishchandra's theorem, the character is on the group, on the compact Cartan subgroup, and the corresponding infinitesimal character, if you look at that parameter, it will be on the Lie algebra of the compact Cartan, that will be, as I said, imaginary. Okay. The techniques we formulated in my previous talk are aimed at constructing invariant distributions or invariant open subsets of G, starting from M invariant distributions on some M invariant open neighborhood of 0 in the Lie algebra of M. M is a reductive Lie subgroup of M here. The distribution so constructed will then be pieced together. So let G be a real semi-simple Lie group. Let's assume that the rank of G is the same as the rank of the maximal compact. We propose to discuss the construction of invariant eigendistributions on G that will eventually turn out to be the characters of the discrete series of G. Since the rank of G is equal to the rank of K, G has compact Cartan subgroups, and all such are mutually conjugate. We fix one of them, say B, contained in K, and denote its Lie algebra by B. All groups of GB are imaginary. We want to start with a non-singular integral linear form on the Lie algebra of the compact Cartan subgroup and associate a distribution to that linear form. Theta lambda is the invariant eigendistribution on G associated to this non-singular linear form lambda. It is going to be a locally summable function on all of the group G. So we need to specify it only on the set of all regular elements of G. It is the unique invariant eigendistribution theta lambda satisfying two conditions which are specified here. The first condition is a formula for theta lambda on the set of all regular elements of the compact Cartan subgroup. On the left side, the delta, which you see here, is the so-called well denominator. On the right side, the sum is only over the elements of the well group of the maximum compact. Psi lambda is the character of the compact Cartan subgroup corresponding to lambda. Only the characters on B which are in the orbit of psi lambda under the well group of the maximum compact K occur in this summation here, and it is an alternating sum. dx is the function which you see here at the bottom. Remember that element x of G is called regular if dx is non-zero. The second condition for theta lambda is a growth condition, sometimes also called a condition of moderate growth or tempered growth. This suprema, so this tempered distribution will be defined later on after we introduce the Schwarz space of the quantity which you see here should be finite when you take this supremum over all the regular elements of G. Though we call it the main theorem of Harishchandra, the important main classification theorem, the famous discrete series classification of theorem, involves these distributions, and it tells you how these are related to the discrete series representations. We will take it up by the end of the third talk tomorrow or day after. Also, it should be perhaps emphasized that it is enough to specify theta lambda on the set of regular semi-simple elements. In the last lecture, we defined something called a completely invariant open subset of V. Open subset V of G. Take an invariant open set V of G. Take any element x of V and take the Jordan decomposition. So we say V is completely invariant if the semi-simple part in the Jordan decomposition also belongs to V. We will now define an elliptic class E of invariant open sets. It will turn out that every invariant open set which is a member of this elliptic class is also completely invariant. We start with some easy definitions. For x and G, take the centralizer of the element in the group, centralizer mx in the group, and also take the centralizer mx of x in the Lie algebra G, then one is the Lie algebra of the other. An element x is called elliptic if it is conjugate to an element of the compact Cartan group, Cartan subgroup, or the same thing is saying that it is conjugate to an element of the maximum compact K. An equivalent way of saying it is that x is semi-simple and all eigenvalues of add x are of modulus 1. Any element x of G can be written uniquely as a times exponential of y, where a is elliptic, y is in the centralizer of a in the Lie algebra, and all eigenvalues of add y are real. the A is called the elliptic component of X. So, what is the elliptic class E of invariant open subsets V of G? What is it? If an element X belongs to V and A is the elliptic component of X, then A expects belongs to V for every X in the centralizer of A in the Lie algebra for which add X has only real eigenvalues. The blue block is to convince you that if V is an invariant open set which belongs to the elliptic class, then V is completely invariant. Given an elliptic element A and given any epsilon, define an open set G epsilon in the Lie algebra G to consist of all X. So I will refer to these V epsilon as small elliptic open sets. Small elliptic G invariant open sets. So later on we will see that any member of this elliptic class can be covered by small elliptic open sets. Covered meaning contained in V and then the union will be equal to all of V. The small condition V epsilon, that condition being a small elliptic open class is imposed so that we'll be able to pass from the distribution on the open set, given open set V epsilon, to a distribution on a neighborhood of 0 in the centralizer of the element A, that UA epsilon. Is that for every eigenvalue, the imaginary part is less than epsilon. Intersect G epsilon with MA, the centralizer of A in the Lie algebra G. That is UA epsilon in the Lie algebra MA. Exponentiate that and multiply on the left by the group element A you started with. That is UA epsilon in the group. In the group MA, which is the centralizer of A in the group G. Now, saturate that group object UA epsilon by the adjoint action of the group G, and that is an elliptic class open set in the elliptic class E. So let me explain that again. See, we were able to see that. Okay. So this is in the centralizer. It's a small neighborhood of 0 in the centralizer of A in the Lie algebra. The centralizer is MA. And then you exponentiate and multiply on the left by A. So that is in the group MA. The group's MA. And now we want to go to the group G, open set in the group G. So you just conjugate by this UA epsilon by all elements of the group and take the union. That is this one. All X such that for every eigenvalue, the imaginary part is less than epsilon. UV being adapted to A if certain conditions are satisfied. So I'll just leave it to you to view, and I will keep quiet for a few seconds. This is again from lecture 1, a nice theorem about what to do with adapted system. Take all the semi-simple elements in your completely invariant open set, The union of the VA gives you all of V. If you have an adapted system UV, then there is a very nice bijective correspondence between distributions theta, which are invariant under G on V, and distributions on U, which are MA invariant, in such a way that you have a good hold the way the center of the invariant algebra acts. By looking at the same for theta A. Moreover, theta is a locally summable function on V if and only if theta A is a locally summable function on U, and the correspondence can be made very explicit. There is a subtle point here which should be emphasized. The idea and the construction here uses a broader differential geometric point of view in the framework of submersions. If you use only that point of view and not use extra data available in the particular Lie group situation, you would only conclude that the distribution theta A is invariant under the analytic group of MA. But invariance here is asserted under the larger group MA, the centralizer of A in the group G, which may be disconnected. The analytic group here could be a smaller subgroup, namely the identity component. Given an elliptic element A in the group and given epsilon, we define G epsilon, an open invariant open set in the Lie algebra G, and also UA epsilon, an invariant open set, MA invariant open set in the Lie algebra MA, the centralizer of A in the Lie algebra G. We also define the open set UA epsilon, and also define the G invariant open set VA epsilon. We now list some easy properties of the class E of elliptic invariant open sets.
So these four lemmas are listing some basic properties of the elliptic class of open sets.
The elliptic class of invariant open sets V in G in the following four lemmas. For small enough epsilon, this UA-VA epsilon is an adapted system. In the group centralizer MA of A in the group G, we define this open subset MA invariant open subset UA epsilon. Take the intersection of this group object UA epsilon with the compact Cartan subgroup B. On the right side, you look at the corresponding Lie algebra intersection. Then you exponentiate and multiply on the left by this element A you started with. These two are equal. Now you saturate this UA epsilon by taking the joint action by G. That is an invariant open set which we called VA epsilon intersect with B. That equals the union of all this while group translates of this UA epsilon intersected with B. Translates only by the while group of K with respect to B. The elliptic class E of invariant open sets is closed under finite intersections. For small enough epsilon, this invariant open set VA epsilon is in the elliptic class. For any elliptic class open set, G invariant open set V, and for any elliptic element A belonging to V, for small enough epsilon, VA epsilon is contained in V. Take an elliptic class open set V. For every elliptic element A in V intersected B, make any choice sufficiently small elliptic class open invariant open set VA delta A to be contained in V, any choice. Whatever the choice, V is the union of all this VA delta A. Moreover, if you choose V to be equal to G itself, then finitely many such VA delta A cover G. We start with a description of two lemmas dealing with some spaces of distributions on a reductive subalgebra M of G, and derives from those two lemmas Harishchandra's main theorem about the invariant eigendistributions theta lambda with the prescribed formula on the compact Cartan and having growth properties. M is the analytic subgroup of G corresponding to the reductive subalgebra M that we chose. Choose the Cartan subalgebra L of this reductive subalgebra M. For the roots of M with respect to L, choose a positive system PML. PML here is a polynomial on L. It is the product of all the positive roots coming from PML. Well, PML is a differential operator. It is the product of these vector fields delta H alpha for each coroot alpha. The regular elements are those where no root vanishes. We are close to stating the two lemmas with just a little more preparation. B is the Lie algebra of the compact Cartan subgroup. The subscript C means complexification. We are assuming that the Lie algebra of the compact Cartan is contained in the reductive subalgebra M. Take a linear form nu and assume that it takes imaginary values on B. That means nu takes real values on the coroots. Assume further that nu is regular. That means nu is non-zero on the coroots. For an epsilon, we already defined this G epsilon and U epsilon. Let T nu epsilon be the space of all M invariant distributions T on U epsilon such that take an element of the center of the enveloping algebra Z. From the center of the enveloping algebra of G to the center of the enveloping algebra of M, there is this homomorphism, and you do a twist with the tilde. That differential operator acts on the distribution T. That gives multiplication of T by this scalar, that is the homomorphism chi nu applied to the element Z. These distributions T should also satisfy these growth conditions on the regular set of each Cartan subalgebra L in M.
Any questions so far? It's just a matter of design which in which I should have, for this particular case of constructing the discrete series characters of the theta lambda. So for that he's doing all this. But all this has to be said so that we can introduce to you the what are all the things which are going to appear when you go to this method of descent, follow this method of descent. And also, I should say I'm sorry for this kind of bedtime stories kind of saying my lecture.
There are these three well groups and these inclusions. The index of the smallest in the biggest is denoted by Pm. The differential equations satisfied by the distributions in T nu epsilon make them locally summable functions which is analytic on the regular set. The statement of lemma 1 is that if a distribution T belongs to T nu epsilon, then T is 0 if and only if it vanishes on all the regular elements of the compact Cartan subgroup. It is a uniqueness statement. If two distributions T1 and T2 coincide on the regular elements of the compact Cartan subgroup, then they coincide everywhere.
So here, as I illustrated with the example of unity principal series, it is important that the nu, let's say, whatever I said, yeah, I think I assume nu is real, so that's important.
So can you explain what is capital M?
Capital M is right. So we are going to choose this capital M to be the centralizer of a semi-simple element later on. But right now, M is any subgroup of equal rank. Okay? M is any
Centralizer of elliptic
equal
element.
rank.
It's a centralizer of elliptic element, or
No, we will make it. I think it would be centralized for any semi-simple element because we want to deal with also non-compact Cartan subgroups, but for a while let's postpone this.
M is.
I have still not chosen any A for this.
But capital M is playing.
Capital M is no Lie algebra. First I chose the Lie algebra. M of equal rank containing a compact Cartan subalgebra. And then the M is the corresponding analytic subgroup.
Lemma 2 is an existence result, existence assertion. The dimension of the space T nu epsilon is equal to the index of the smallest well group in the biggest well group. We will take up the proof of these two lemmas later on, but for the while we will assume and see how to use them to draw conclusions about Herschel's main theorem of the theta lambda. We will begin with the uniqueness part of Herschel's theorem.
I think the A will be assumed to be elliptic as the question because we want the equal rank subalgebra, reductive subalgebra to have a compact Cartan. We want
So it is centralizer of the elliptic element.
we will be choosing to be an elliptic. Take this centralizer.
In the form of the assertion in the lemma 3 down below. Let lambda be a regular integral linear form on the Lie algebra of the compact Cartan subgroup, compact Cartan group. Let V be an invariant open set in the elliptic class, theta an invariant distribution on V which is an eigendistribution for the center of the enveloping algebra of G. Suppose theta satisfies the growth condition as in Harishchandra's theorem, and that theta is 0 on the regular elements of the compact carton. Then lemma 3 asserts that theta is identically 0. Well, these are the key ingredients of the proof of lemma 3. So it suffices to prove that for every A belonging to V intersected B and small enough elliptic class open set VA epsilon, we would like to prove that theta restricted to VA epsilon equal to 0. There are these important facts for invariant distributions. Define this small enough elliptic class invariant open sets VA epsilon as before.
Anyway, these are all things we said and we saw in the first lecture. There is an error, and I missed one extra factor here. So I will show the extra factor at the end of the lecture. Let me not interrupt, because this is an MP4 file, and interrupt, do something else and come back. So I'm going to lose a lot of time. So I will show it at the end of the week lecture.
Remember that they're all completely invariant. As we define it. Restricted to VA epsilon is 0, it is enough to prove that theta A equal to 0 by looking at that equation 2.5 there. By the hypothesis of lemma 3, theta B is 0 for every B in V intersected B prime. So theta AH is 0 for every H in B prime intersected UA epsilon. So theta A is 0 on UA epsilon by lemma 1, which is a uniqueness property as we mentioned earlier. That is, if a distribution belongs to T nu epsilon, and if it is 0 on the compact carton, then it is 0 everywhere. This completes the proof of lemma 3. We continue with the assumption of lemma 1 and lemma 2 and indicate how to deduce the construction of Harishchandra's distributions theta lambda. For each distribution in T lambda epsilon MA, define this analytic function phi t on B epsilon by this formula here. By lemma 1, this mapping T going to phi t is the linear injection of T lambda epsilon MA into the vector space of all analytic functions phi on B epsilon with this alternating property and with this expression which is alternating, involving only the well group translates of lambda here.
Well, there was in the formulation of lemma 1, the T lambda, there is a lambda there, T lambda. The lambda was used to give some, our distribution should satisfy some, like an eigendistribution, it should satisfy some differential equations with respect to the center of the enveloping algebra. Some elements of the center of the enveloping algebra. MA coming, which themselves are coming from the center of the enveloping algebra of G. Okay, that was the way it was set up. So that, and if you use those equations, it will follow that only this exponential S lambda, only those will occur in this expression for phi.
We saw an inclusion of 3 well groups, and what you see here on the right side is summation over the largest well group. There is also this coefficient CS, but we will see that CS will be constant on cosets of the smallest well group. And also note that the lambda here is the same as the lambda in T lambda epsilon. But the dimension of this space of analytic functions u lambda epsilon, as in the previous slide, has the dimension of the number of courses of the smallest well group in the biggest well group. And so by lemma 2, this map T going to phi T is an isomorphism onto u lambda epsilon. Let me point out that this psi S lambda is a character on the compact Cartan subgroup, whereas this exponential here is a character on the Cartan subalgebra. Here we are taking,
I hope you remember that we are assuming lemma 1 and lemma 2, and then we are trying to prove Heisenberg-Rein theorem about the construction of the theta lambda. For that purpose, we stated a lemma 3, which really is similar to the statement of the Heisenberg's theorem, but on smaller elliptic class, open sets. We proved lemma 3 assuming lemma 1 and 2, and now we are trying to deduce Heisenberg's theorem from this.
the value of the character psi S lambda at the point A in the compact Cartan subgroup. The expression you see here on the right side obviously belongs to this space of analytic functions u lambda epsilon. If you call it phi TA, then obviously there is a distribution TA in T lambda epsilon whose phi TA is that expression. The NA here is the centralizer of this element A in the Lie algebra G. The corresponding analytic group is a subgroup of the group G, and it fixes A and the conjugation. But the stabilizer of the element A in the group G is a larger group in which this analytic group is sitting as the identity component. With that observation, if you take a look at this expression again, you can conclude that this distribution TA given by lemma 2 is in fact invariant under the stabilizer of A in the group. The NA invariant distribution TA on UA epsilon gives rise to a G invariant distribution theta lambda A on VA epsilon for B belonging to a small open neighborhood of the point A in the compact torus B. Observe that in the first equation, if you replace B by a conjugate of B by an element T belonging to WB, the well group, the left side changes sign by epsilon T. On the right side, if you conjugate B by the same well group element T, the conjugate of B may no longer be in that small neighborhood of A.
But the purpose of this screen is, you see this equation, that equation. This equation here is claimed that is valid for B in this neighborhood of A. Okay, in this neighborhood of A. The purpose of this screen is to show it is valid for a larger neighborhood of A. In fact, you intersect this VA epsilon, that in the group G we have that elliptic class open set which we constructed given A and epsilon. So that you intersect that with the compact torus that is going to be larger than this. So the purpose of this is to show that the equation is actually valid for the entire intersection of V epsilon with the compact group B. So let's go to the next screen now. I see that video 3 ended there, video 4.
It remains to prove lemma 1 and lemma 2. First, let us begin with lemma 1. Start with a distribution T on U epsilon. So T belongs to T nu epsilon. And we know that TH is 0 on the part of the compact kathon intersecting that U epsilon. The distributions in T nu epsilon satisfy two conditions. One is a growth condition which is similar to the growth condition of theta lambda and Heshendra's theorem. The other is some differential equations coming from the center of the enveloping algebra and involving this eigen character on the center given by this nu. It must be shown that for each Kathon subalgebra L in M, T is 0 on the regular elements of L intersected with U epsilon. If L were theta stable, then L is the direct sum of L intersected with K and L intersected with P in the Kathon decomposition. The intersection with K is the part where all roots take imaginary values, and the intersection with P is the part on which all the roots take real values. That is the decomposition Li plus L, which you see there, but it can be defined for any Kathon subalgebra of G without any reference to the Kathon involution. The proof of lemma 1 uses induction on the dimension of Lr. We may assume that L is not conjugate to the compact Kathon B. So dimension of Lr is positive. The linear form nu, which you see here, is on the compact Kathon. It's a linear form on the compact Kathon. Is not on L. But you choose any mu belonging to L star, the dual of L, such that both mu and nu give rise to the same infinitesimal character of the center of the enveloping algebra. Slightly relaxed regularity condition is relevant. Let us look at the part of L where no real root of ML vanishes. We call that L prime R. The differential equations coming from the center and also the fact that the nu is non-singular imply that the left side which you see here is a linear combination of these exponential functions. But these coefficients will of course depend upon the connected component. We have to prove that these coefficients are 0 for all well-group element S and all connected components. We will briefly recall this result from lecture 1. The context was the following. You have a distribution on the group. It is a locally summable function. It is analytic on the set of regular semi-simple elements. This analytic function on the regular set satisfies, it is an eigen function for the action by the center of the enveloping algebra on the regular set. Then the question is, as a distribution on the entire group, does it satisfy the same differential equations? Heshendra's beautiful answer is the following. You see this phi LP here. It is the product of the value denominator on L with respect to the P and the analytic function on the regular elements of L. The statement here is that this analytic function on the regular elements of L, where there is no root, if you take any root, real or complex or imaginary, whatever, if you take any root, the corresponding character does not take the value 1 on the element A. This notation L prime or is a slightly relaxed notion of regularity. We require that psi alpha does not take the value 1 for the real roots. The function phi LP, which is analytic on the set of regular elements.
So the rest of the statement is that is just recalling. Okay, it says that it actually extends as an analytic function to this for the weaker notion of regularity, and also when you differentiate with respect to the differential operator, work by LP that extends continuously to all of the Cartan subgroups. And if you do this for two different Cartan subgroups, they do not have any connection at all. Two random Cartan subgroups in G. And if they happen to intersect, then all the intersection is continuous extension coincides. Okay, so let us go to the next slide.
This Lie algebra SL2R plus the Lie algebra of the Cartan subalgebra L1. This man a reductive Lie subalgebra whose semi-central part is this SL2R. This reductive Lie subalgebra has two contingency classes of Cartan subalgebras. L1 belongs to one of these two contingency classes. The Lie algebra A, which you see here, is the three-dimensional Lie subalgebra of G, isomorphic to SL2R, the Lie algebra SL2R.
So, as I said, the proof proceeds by induction of the dimension of the split part of the Cartan subalgebra. So, we assume the induction hypothesis. We assume it is true for another Cartan subalgebra, for all of the Cartan subalgebras where the split part has a lower dimension, and then we are trying to now do it for L1. So the idea is to choose an SL2. Given this L1, the idea is to choose an L2 where actually the split part dimension goes down by 1. So that's possible. That's possible because L1 is not conjugate to the compact Cartan. It is conjugate to the compact Cartan. There is nothing to prove. So L1 is not compact, and it's a general fact that you don't even assume that G is a compact Cartan. G is any real connected semi-simple ego is a fact that there is a notion of a fundamental Cartan subgroup. That means that the split part has the lowest dimension for the fundamental Cartan. The split part has the lowest possible dimension. So the general statement is that even for any real semi-simple Lie group, even if it does not have any compact Cartan subgroup, if you choose a Lie subalgebra Cartan, if you choose a Cartan subalgebra which is not the fundamental Cartan, there is always a real root. There is always a real one real root to construct another Cartan subalgebra that is called L2 here in this screen. Such that for L2 the split part dimension is 1 less, and we know the vanishing on L2.
The equation in 4 gives you the intersection of the SL2R with the Cartan subalgebra L1. So it's all those diagonal matrices with real entries in SL2.
Sorry,
Statement 1 here is what I said.
Sorry, is this what is called the Kelly transform? Is this what is called Kelly transform?
Oh, no. This is,
You know, I mean,
you take a, given this L1, there is a real root. Take the real root and take the corresponding root space for the real root, the negative root. Okay? G alpha, G minus alpha, and H also. Take that three-dimensional simple, which is intersect with your real form. That is an SL2 now. In that SL2 has two Kaplan subgroups which are not conjugate at all.
So you replace the split one by the compact one, and this is what is called Kelly transform.
Yeah, this is exact. Yeah, you're right.
I mean,
Within SL, but we don't need it. We don't need it. I just
the
need the
notion of
SL2
the
as
Kelly transform changes Kaplan subgroups by this process that you are describing, and maybe it allows you to go from any Kaplan to any other Kaplan.
So there is a way of saying it using the Kelly transform as well. I don't know whether I'm saying it in the next screen or not. But it's just a very simple statement. So
What
what
is
SL2
one
is
Kaplan to any other Kaplan by just doing something in SL2R. I think this is what is called theory of Kelly transform.
that's true. It's called Kelly transform.
Earlier, the L1 plus the SL2R is a reductively subalgebra. It has two conjugacy classes of Cartan subalgebras. We choose a Cartan subalgebra L2 from the other conjugacy class such that when you intersect with SL2, you get those matrices which you see in equation 5. We are seeing here a part of the last screen and the screen before that. The three-dimensional simple real algebra A, we got it by choosing a real root of L1 called the real root beta. If you take the Lie bracket of any element of A with the kernel of beta, you will get 0. So the kernel of beta is actually the center of this reductive real algebra L1 plus A. And this center will be contained in any other Cartan subalgebra of L1 plus A, in particular L2. From the distribution T, we got an analytic function on the set of regular elements of any Cartan subgroup, but after a certain differentiation there, we actually extended it continuously to all of the Cartan subgroup. That was called psi L. This extension for any two Cartan subgroups L1 and L2 coincide on the intersection. Coming back to our induction hypothesis and trying to push it from L2 to L1, the induction hypothesis, this psi L2 is 0. In particular, it is 0 on the subgroup of L2 corresponding to the center. But the center is contained in any other Cartan subgroup, in particular, it is contained in L1. So psi L1 is 0 on the center. I'm also reproducing here some statement involving those connected components. We have to prove that those coefficients for any connected component are 0. We will describe very soon more explicitly these connected components. If you take any one of these connected components, take the closure of any one of these connected components and intersect with the center, there is going to be a codimension 1 cell, or rather the closure of a codimension 1 cell containing the center and containing the closure of the connected component. So this psi L1 is going to be, excuse me, this psi L1 is going to be 0 on this intersection with the center. B is the Lie algebra of the fixed compact Cartan subgroup. We can conjugate L1 inside M such that the imaginary part of L1 is contained in that B. Let M1 be the centralizer of the imaginary part of L in M. Then the imaginary part of L is the center of M1, and the real part of L is a Cartan subalgebra of the bracket of M1 with itself. The M1 here is the centralized.
Okay, so this screen it just it describes the connected components. You know, it describes the connected components. It's so if I go back. I have this. Somewhere I said I wanted to describe the connected components.
Of the imaginary part of L, then the L here is like a split Cartan for the M1. Now let us apply all the considerations of a reduced root system. So you have these positive chambers for each choice of a set of simple roots for the reduced root system. The connected components gamma we talked about earlier are precisely all these epsilon plus these positive chambers. For a reduced root system, you have this notion of reduced while group, the group generated by all simple reflections. The reduced root system, of the while group of the reduced root system acts simply transitively on the collection of all these connected components gamma. If you fix a system of simple roots S, then any linear form tau, which is real valued on the real part of the Cartan subalgebra L, you can bring it to the positive chamber corresponding to S by acting on it by an element of reduced while group. The choice of the Cartan subalgebra L2 is described more intrinsically here without any reference to SL2. L tilde here
This is the
is our L2, really. The L beta here is contained in L, and it is also contained in L tilde. L tilde is the L2. So this L beta is the center. The statement of the lemma is also something we mentioned earlier. It gives a nice description of all those connected components gamma, and the description includes also the intersection of the closure of this gamma with the center. These intersections are of codimension 1. This is already noted. Take a connected component gamma in U epsilon intersected L of the complement of root hyperplanes corresponding to real roots of M1L. So for any such gamma, we have to prove CS gamma is 0. These components gamma are in bijective correspondence with choice of a simple system of roots for the restricted root system of M1L. So we are doing this choosing L equal to L1, take the closure of such a connected component gamma, intersect with L2, take the closure of gamma and intersect with L2. That intersection contains a nice codimension 1 cell on which the induction hypothesis can be applied because it's contained in L2 as well as L1. So we can conclude that the coefficients should arrange in such a way, should arrange themselves in such a way that the sum of those exponentials with coefficients which equals this psi L1 on that gamma closure must vanish on that codimension 1 cell. The sum of those exponentials with those coefficients, which stands for this psi L1, must vanish on the codimension 1 cell in L1. I was imprecise when I mentioned the sum is a root hyperplane for beta and it is a codimension 1. Exponential functions of L beta with different exponents or linearly independent. S mu and T mu have the same restriction to L beta if and only if S equals T or S equals S beta T. Observe that S mu on H alpha is non-zero as mu is non-singular. This leads to the fact that Cs is not equal to 0 if and only if Cs beta S is not equal to 0. Suppose that Ct is non-zero for some t in the ambient well group WLC. Our gamma is essentially the dominant chamber in the restricted root system for a choice of simple roots S. In the well group generated by reflections S gamma for gamma belonging to S, choose an element S prime so that the corresponding S prime T mu is dominant. Then Cs prime T is also non-zero by the above fact. We are close to completing the proof of lemma 1. In lemma 1, there was this distribution T belonging to T nu epsilon. It satisfies some growth conditions and it is an eigendistribution also. The growth conditions prohibit any positive exponent occurring in this exponential. So S mu h is less than or equal to 0 for every h in that positive chamber, which is really the connected component gamma. No positive exponent if Cs gamma is non-zero. Look at this S prime T mu. S prime was chosen so that S prime T mu is dominant. But now we are saying that we cannot have a positive exponent, positive number in the exponent because Cs prime T mu is non-zero as well. So S prime T mu beta is 0 for every simple root beta, but that contradicts the regularity of mu. That completes the proof of lemma 1. Lemma 1 is complete. So if we prove lemma 2 also, then we have this Harishchandra's theorem. We will take up lemma 2 in the next lecture, maybe tomorrow or day after.
No, tomorrow, it will be tomorrow. So I said somewhere in the middle that I made a mistake and I missed one factor. Do you have time to see it now or do you